Yeah, this is a training sort of in three parts. Um, I'm going to take the lead on the last section on our last tool. I've already introduced myself and the center at the beginning of this, so I'll skip right through there. I want to set the stage for the conversation for this last tool by sort of contextualizing it in relation to other existing tools in the same genre. So I've shared presentations and delivered training on Hypershell in the past that sort of covers a lot more territory. For today, I'm not going to do a lot of that, and I'm going to rely on the context that Bill has provided earlier in the conversation around high throughput computing, generally speaking. And then specifically, a lot of what I'm going to do is going to be in direct relation to what we've already talked about with GNU Parallel. So it's meant to kind of be a contrast. So we won't necessarily sort of agonize over philosophical things quite as long as I might otherwise have if we didn't literally just talk about GNU Parallel. So yeah, I want to talk about this last tool and the features that it provides relative to the features and capabilities of what we've already talked about today, and demonstrate a few things. So far we haven't done anything like this, but I have things set up and a reservation on one of our newest campus clusters. So I'm gonna share both my presentation materials and hop over to terminal and kind of do some live demonstration as we go along. Okay, so motivation, too long, didn't read. If you end the conversation now, what, and a kind of overview. Um, why use a workflow tool at all? Why not use the main scheduler? I would normally kind of spend a lot of time here in having a conversation about workflow tools in general before speaking specifically about any one tool. But I think Bill did a really good job of sort of introducing this earlier. But just to revisit this in a nutshell, site administrators don't want you running millions of jobs. This sort of depends on what HPC center you're at. Some are more tolerant than others. I know the national labs, especially the leadership class computing facilities, are very, very strict about the minimum size of a job and what they're really trying to cater to. Here at Purdue, we actually have very liberal policies. You can queue up 5,000 jobs and get away with quite a lot before you run into any of the sorts of issues that Bill was speaking to early on. But nevertheless, there's still kind of fundamental limitation to sort of what the main scheduler is both designed to do, but also it's not really about what it's designed to do. It's more about practical limitations when, this is serving the needs, in our case, of thousands and thousands of users, right? We might have hundreds and hundreds of people running jobs at any one moment. And it's not really fair to ask one scheduler to manage all of that. And so part of the conversation here is not really about the tool itself. It's about getting out of that main scheduler if for no other reason, just so that you're sort of isolating that throughput. And filling up the database, not all schedulers really have this problem. We never ran into this before, but uh, in recent times, for the first time ever, we're actually having a conversation about rotating one of our cluster databases just because it is so full that it's impacting throughput. So like there's the potential to lose your job history because we've rotated that. There's site-wide throughput. I know Slurm is the most popular scheduler on a lot of sites, at least here in the US. And they've really tried to move in the direction of supporting throughput, but nevertheless, there's still a rate limiting issue. Um, and even just on the user side, uh, in relation to these, you don't want to be rate limited. Like if your workflow could run and the only thing impacting the throughput of your workflow is the sort of rate limit policy on the main scheduler, then that's sort of disadvantageous. Okay, so what I normally kind of lead with, just as sort of a tongue-in-cheek reference here, is, user comes to our office hours and says, "Hey, I want to run my job a million times. Can you let me do that?" And it starts out with me saying, "Yeah, about that." Um, there are a lot of tools that kind of fit in this genre, and we have built our own, and I'll get to that in a second. But in a nutshell, we've got a project that it's not, I'm the main developer of the project, but there's been a lot of people that have sort of been in the orbit and contributed conceptually and ideas, and there's a lot of researchers both here on campus at other universities and on our Anvil cluster over the last 5 years that have sort of contributed to testing the needs and function of this. What we've got is a high throughput computing command line tool that is inspired by the existing ecosystem of tools similar to GNU Parallel. There are others that I'll mention. Um, so yeah, this is something that we wrote, and it is cross-platform. Why a new tool? So as Bill was suggesting, there's kind of a trade-off, and certain kind of dimensions to this ecosystem of workflow tools cater to different capabilities. So there's some that are really more about the workflow definition. So that's things like SnakeMake and other make-like tools that are based on the file system to define dependency relationships. And there's things that combine that with execution. For the purposes of this conversation, I'm going to sort of limit the kind of boundaries of this to everything that fits in the genre that you might put GNU Parallel in. And so I've got that right at the center of this very fuzzy visual that is supposed to be relating a number of different options that are out there in the landscape of tools. On the horizontal axis, you can kind of roughly think about that in terms of scalability, like how big can you go? And on the vertical axis, it's like how complicated does it get, both as a user and as an administrator. So what we're trying to solve with this is have the ease of GNU Parallel to get started, and taking that inspiration of what it looks like to just be a simple kind of queue of shell commands, while sort of building on top of that from the ground up some capabilities that bring it a lot closer to something like HT Condor. All right. So what are we lacking that we might be interested in? So we touched on a few of these when Bill was talking about GNU Parallel. So things like scalability and retries, and some file system limitations, some throughput problems. So we're going to solve those by implementing this notion of task aggregation. I'll get to all of these in turn as I go along. But we want greater throughput, and we're going to do that through aggregation. We want fault tolerance. If a node goes away, we don't just want to leave it dangling. We actually want to recover and bring back compute resources somehow, and have something called task stealing, where we take things that got orphaned by a failed node and redirect them to new resources. I want better task management. I want to be able to look at my history of tasks and be able to do very rich, compelling things easily, and manage a large fleet of tasks outside of the main flow. I want elasticity. So I don't want a monolithic start to finish situation for my large scale workflows. I want to be able to go big, but I also want to go to zero. A lot of systems, especially at the national labs and in the Access ecosystem, right? You have service units, and we don't want to be wasting our service units unnecessarily, just scaling things. We want that to go to zero, but then come back automatically. This one maybe isn't important, but cross-platform, the actual initial reason that we built anything in the first place was a particular project with a research group where they had a vendor application that only ran, like, it was just an x86 Windows executable that was completely inscrutable. We had no access to it. Like it had to run, and it was actually somewhat pathological in the sense that it would only run one at a time on a Windows host. And so we needed to like somehow orchestrate this queue of things under Linux, but the application needed to run inside of a Windows VM, and we couldn't tolerate, it was so heavy to try to stand these up. We wanted the VMs to come up across the cluster and have them still work asynchronously, and try to have this high throughput cluster that sort of spanned multiple operating systems. And so nothing out there really did that, that didn't involve building the whole world yourself. I'm interested in ergonomics. I want something that is built with this kind of workflow scenario in mind. Something that I've noticed is that there are tools out there, especially in the Linux world, lots of command line tools that serve different functions written with different sort of use cases in mind. But for the researchers that I work with, a lot of times I'm going to describe them as being user hostile in the sense that they have very esoteric meaning options that have very strange behavior, and it becomes cumbersome for the researchers to navigate all the different corners of the tool. And having not just a clearer picture, but even just a reduced surface area of complexity has value. And then one last thing is the idea that this is also a library that you can take and embed in your own project to provide this sort of functionality inside of some other application. So continuing with the TLDR, there's a GitHub repository that you can go star and look at the source code for this thing. We host the docs and reference material, release notes, and everything on Read the Docs. At the moment, hypershell.org just redirects to the docs. I don't have a lot of spare time in the day I'm not exactly a web developer. So proper website coming soon. And I also have a Discord server if you're interested in chat or if you want to post questions. Okay, so installation. This is also a Python application. Referring back to the 14,000 lines of Perl, this is 10,000 lines of Python. The fact that it's Python is not important, unlike SnakeMake, where Python is sort of front and center and a requirement for you to author and define a workflow. The fact that this is written in Python should not, like that is just an implementation detail. The goal here is that as a system tool, right, almost nothing Python is sort of leaked to the user. So users are likely to want to run the tasks they're going to run are Python. And so we don't want any overlap there. This is on the Python package index and on GitHub. You could pip install it. I actually recommend that it go inside of a dedicated virtual environment. You could do that with Conda. You could do it yourself with something like pipx. Over the last year, I've transitioned almost entirely over to something new called UV. I very much recommend it. This isn't going to be, too much of a, me waving my arms around trying to advertise for UV. But if you don't have this on your system already and you need to install this tool yourself as an unprivileged user, I highly recommend that. There is also a brew tap if you're on Mac or Linux. We won't really get into this, but one of the values here by decoupling a lot of the components in this system is that you can span multiple servers. And so you can have the server running somewhere else, clients running on nodes, and you can sort of interact with the system from your local laptop. So you could brew install it on your Mac. Something that I've spent the last 6 months on ever since the supercomputing conference back in November is trying to sort of steward this into the Linux packaging ecosystem. And I want to give a really quick shout out to the folks at Alma Linux. One person in particular inside of Alma has just been awesome at helping me navigate this. And he, as of last night, literally last night, Hypershell is now in EPEL 10. I also have an acquaintance inside of Ubuntu's HPC team. So Debian and Snap coming soon. There's also Docker images. This is not really useful as a Docker or an Aptainer image on its own because its whole reason to exist is to run um, other programs, and so those other programs would have to be inside of it. But if you're containerizing your own thing, you could roll this container into yours. Anyway, so lots of different ways to install. We have it as a module. I highly recommend admins on the HPC system install Hypershell as a module. There's certain considerations that are really important at exposing um, certain features that it's just easier to do that centrally. In particular, the fact that this is written in Python and Python is so ubiquitous all over the system and with the users, there's a mechanism here to harden it so that it can't break. And that's easiest to have a site admin sort of deal with. For myself, I can just module load. Okay, to start off with, I want to begin with a Hello World example that is kind of taking us from where we started with the GNU parallel one-liners, just to kind of have sort of a common starting point and map everything that we talked about there onto this new tool, and then from that grow in to areas that GNU parallel really kind of struggled with. So to start off with, we do have the, let's see, Git repo. So if you haven't already, a lot of what I'm going to do is captured in these sections. And everything I've talked about so far is kind of in this top level README. So we're going to start out here. Almost everything is filled out somewhere in the middle with some of the like database management stuff. I haven't really completely completed filling this out. I'll commit that later, so I apologize. But we'll talk about it here, and it'll be in the recording. Okay. Um, Right, so hello world. I'm going to jump over here to my terminal. So I'm logged into our Gauchi supercomputer here at Purdue. So this is a campus system. It's about 300 plus CPU nodes. And then we've got a bunch of NVIDIA H100s on an AI partition. And so a lot of what I'm is in the material is going to submit jobs. Just in the interest of our conversation, I'm not going to submit jobs and then wait for them to run and keep throwing away my allocation. So here on my second window, I've already got a 8 node allocation. So we've already kind of talked about Slurm. So just an srun hostname is showing me here are my 8 nodes. And then in this third window, um, I will, it died because I didn't give it a time limit, so I'm going to kick this off and have it, I don't know, 120 minutes. There we go. Okay, so I've got my GPU allocation over here. I'll come back to that in a second. So I have a module, so I've already loaded Hypershell. I'm not going to sort of demonstrate installing it just in the interest of time. So we'll just kind of assume its presence here. There's 2 executables to care about. The main is HS. If you run HS help, you'll get sort of a summary of all the different subcommands. There is also a manual page that has more detail than we could possibly go into. The other is this HSX, which is just shorthand for HS cluster. So this is where we're starting off. If I go to the first example, which I don't really need to go into the directory, but we haven't configured anything yet. So if we run this, this is kind of like the very first one-liner we ran with just the echo. We have taken inspiration from some of what GNU Parallel does. We don't have that funny colon syntax that does the sort of multiplicative or additive combinatorics for all of the inputs. It just reads lines from a file or over a pipe. So the simplest possible example here is just a first in, first out queue. We're getting a warning that we don't have a database configured. We'll get to that in a minute. If you don't have a database configured, then this is entirely in memory. So as the thing is running, if for whatever reason it comes down, all of that information and state is lost. This is just a transient instance. But just to kind of set the stage, here's the sort of hello world of running the application with the cluster. Okay, so that is getting started. Oh, the for the cluster, we don't take the command line template isn't positional arguments. A lot of what is kind of very syntax heavy in GNU Parallel are just straight command line options. A lowercase t for the Hypershell cluster entry point means template. And the naked curly braces here are exactly the same in GNU Parallel. So essentially, the seq Unix command just gives you a range of numbers 1 to 4 here, and we're just piping that in and re-echoing them out. Okay, so let's do something a little bit more complicated. Let's introduce parallelism and explicitly acknowledge the fact that we're running in memory. So going out here to basics, I've got, even though we're kind of doing this in a transient fashion with the sequence command, I've committed what the input should be into the repo. In this case, instead of 4, we're going to go through 12 and introduce parallelism. So the uppercase N here is the number of parallel task executor threads. So this is how many workers, like how many things at a time are we going to do? And I've introduced a sleep into the command template just so that we can kind of watch the cadence. The dash dash no db is going to explicitly acknowledge the fact that we've not configured a database and suppress that warning for us. What I want you to notice is the fact that these kind of came in bursts. So the first 4 came through, and then the next 4, and then the next 4 with in 1 second intervals. The point here is just to kind of illustrate that parallelism and that it's happening. Okay, so let's keep ramping up the complexity here, and I want to introduce some additional stuff around templates. So again, very heavily inspired by GNU Parallel. It is not identical to GNU Parallel. It is only inspired by some of the curly brace isms that are provided, in this case, around file paths. So in our next example, I'm going to go here to basic templates. And just to kind of sort of illustrate this, for like maybe 60 or 70% of our users, the most, like, we don't need a complicated workflow system. We don't need ordering. We don't need dependency management. We don't need explicit resource constraints. All we're really doing is mapping inputs to outputs. This is very common in the bioinformatics space. This is common in well, not the LLM stuff, but 2 years ago, what I would say is the common sort of AI workflow where we are training. We're running a large campaign of experiments, and we've got 1,000 permutations of a model, and we're mapping input hyperparameters to output model weights. This mapping of in to out is probably the most ubiquitous thing that anybody wants to do. So in this example, I've got 12 files. Each one is 10,000 lines. And if I look at the first few lines in 01.txt, essentially what we've got is a whole bunch of hay in a stack, and we're going to find a needle in the haystack. So if I were to say grep for needle in this 0, 1. There's only out of 10,000 lines, there's the needle. Okay. So how do we operationalize this with uh, the tool? You could do the same thing with GNU Parallel. Um, we're just kind of leading through where we started there, and we'll kind of continue to ramp up the sophistication as we go along. Let me look at the questions real quick because I just noticed those. All right. Okay. Yep. So here what we're doing is just using the Unix find command to generate a list of those input files with their the full path to those inputs. And we're simply executing them one at a time. Um, the -t for the template, and we have a shell command here. The entire file path will get substituted verbatim with the empty curly braces. The file paths is one of the most common things, so there's a bunch of these. In this case, the / on its own would mean the base name of the file without the full directory, and the following it by a hyphen means that base name less the file extension. So this is going to transform the input file path to just be the name so that we can create the output file path. And we can even throw on a -n2 there. And we don't see any output. I haven't gotten to configuration at the moment. We haven't configured a database. We also haven't configured logging. The logging level by default is warning. So in this case, we weren't really given any feedback about what happened. If I look in output, we've got those, and I can say there is all of our 12 needles in 12 haystacks. All right. Cool. There is an entire page dedicated to the template patterns that are available. I just use one of the file path. Argument slicing, similar to how you can specify a number with GNU Parallel. This square bracket notation inside the curly braces allows you to slice into that argument vector. Indexing starts at 0. This is literally, if you're at all familiar with Python, this is the only place, this is one of the only places where Python kind of leaks out. Whatever the syntax would be in Python to slice into a list, you can invoke that. So you can do things like -1 means the last one. 1:3 means the second and third argument. So it's not inclusive of the last one. You could say the last 4, or the -2 with the trailing colon would be the last 2 arguments on the line. Or even do wacky things like : 2 to do every other. You don't really need the shell expansion if you're in Bash on a Linux system. You can just use your standard like $ parentheses or backticks. But this is a little bit more explicit and portable depending on, well, it's just another way of doing shell expansion. And then you can actually have full Lambda expressions where you can, again, this is one of the only places where Python leaks out. You can include whole Python lines, and those will be evaluated, and whatever sort of comes out of that will be substituted into the command. Okay, so let's talk about some other features that we're going to borrow from legacy tools. And one of them that I'm kind of fond of for its simplicity is just marking which thing failed. So we're going to simulate that by just putting true and false lines. So Unix has these the Unix shell and Bash, it has this really funny thing where there's actually a program called true, and the only thing it does is return 0, which in most programming languages is falsy, but in shellisms, the exit status 0 means good, and anything non-zero means bad. And the only job of the false program is to return non-zero. Everything in Hypershell assumes that If a program exits with 0, everything is great, or as expected. If it's non-zero, then that means that the task failed in some fashion. So like failure is denoted with whatever the exit status of the program was. Um, there is a tool that we've had for over a decade that comes out of the bioinformatics community, if I recall, was just literally excised out of an application called Trinity called Parafly. Parafly is I consider it venerable because of its simplicity and it sort of being unapologetic about doing one thing and just that one thing. And one of the features that it has is that it will just act as like a filter, and you can provide a file path for where you want failed tasks to go. So again, we haven't really done anything about retries or more complicated cluster arrangements. We're still sticking with something relatively simple. So if I go to let's see, basic failures and look at my input file. I've still got my sleeps from before, and we're just echoing out a number to indicate that we did something, and we can sort of signify which task it was. Notice that line 7 ends in false. So if we were to run this, not 11 of these would be considered successful, and one of them is going to be considered a failure. So we're going to say task in, um, and see what are we including right now? Let's just do, 2 at a time, and uh, no database, no confirmations, and we're going to say fail is task fail. So if we run this, again, we haven't done anything with logging. We see our outputs, they just all stream together. We get a warning. So all of the numbers are written as standard out as data. The log messages are written as standard error. So if we had redirected this stuff, which we haven't talked about output management yet, um, the only thing that we would get is that one warning that that task failed. A couple of things to call out here. One is, I think this is the first time we've seen it. Tasks are denoted with a universally unique identifier. So unlike GNU Parallel, where jobs are tracked by a relative integer ID based on the input, and that can cause some issues around like how you're executing the flow, whether or not that integer is consistent between the previous run and the current run. In this case, we have universally unique identifiers. This is going to be very, very helpful later on in our logging output. This is probably the best case scenario you'll ever see for grepping for your out for messages that have to do with your job. If you just grep all of the logs for that UUID, every message that has to do with a certain task, you will recover all of those sort of events in the workflow with that UUID. Okay, so if we look in task failed, there's our one line. And the nifty thing here, again, we're still very, very simple. But what I love about this is the notion that this is kind of acting as a sieve. And if I've got 10,000 inputs and I'm really not worried about fault tolerance, it's not likely that anything is going to fail. If it does, it's probably transient in nature. That's often the case. And I've got a list of my failures that's like maybe 2 tasks. Um, I love the idea that you would take this and feed it right back into the same program as sort of a crude retry mechanism. So we have way more advanced capabilities around automatic retries of failed or orphan tasks. But at this level, this is I don't know, kind of nifty in my book. So we'll talk about retries in a second, but one thing that you could do is just feed it back into the program. Okay, Let's start scaling up. So one of the things that I wanted to talk about is scalability. So let's run this as a job script. To start off with, we're just going to do something similar to what we did before with GNU Parallel, where we ran many tasks inside of a single node. So essentially, all we've added to this is just wrapping this in an allocation. On our clusters, or at least our newer clusters, you'll have to modify this for wherever you're running it. Here, I've just got some fictitious lab that you're a part of, so there's your account. We're running it on the CPU partition, and our QoS is whatever the normal QoS is, and we are just asking for 42 cores. So we load Hypershell and we run our tasks.in. Everything is basically what we just did a second ago. Yeah, not really much to see there. Let's talk about capturing output. Again, we haven't really gotten to configuration yet. Um, Most things in the Hypershell system are a configurable parameter, and the vast majority of those can be set either as an environment variable or as a parameter in a file. There's a few things that are environment variable only, and one of them is something called the Hypershell site. When we were talking about snakemake, there was a mention of this hidden snakemake file that is in whatever the working directory is that you're executing the flow. Um, by default, your default site is going to be the Hypershell folder in your home directory. If you've not defined the variable, if it's running as root, because it's maybe you're running this thing, we haven't talked about this kind of thing yet, but if you're running it as a systemd service on a Linux server as root or inside of a container, then it'll be under var lib Hypershell. But this is something that you might want to put in your job script if you've got a lot of output that you want to capture and you want to make sure that that's going to the Scratch file system and not your home directory, which may not be as tolerant of lots of relatively small files. Then in this example, basically what I'm doing is setting my Hypershell site environment variable to the current working directory. And I'm doing that in concert with a command line option called -- capture. So with GNU Parallel and with Hypershell out of the box, if you've not done anything, all standard out and standard error from your tasks are just going to flow back to the main process in line with whatever TTY or however you're redirecting outputs from the parent process. So all lines are going to be essentially line buffered and just flow together. And if you don't have a lot of output, then that actually can be advantageous for large scale workflows. If you've got some other means of differentiating lines, if the only thing you're looking at is logs and the logs are differentiable, then that might be more efficient. But for some tasks, if either you can't change the code or there's a bunch of output and it's sort of structured and it would just be all garbled if it flowed together. We want to separate out that. And in the parallel examples, we just use shell redirects. You might use like curly braces with the pound sign to have that file path denote the task ID. There's lots of sorts of things that you can construct in the command template pattern. Something that you can do with Hypershell that is going to have a tremendous advantage here in a minute when we talk about the database and distributed workflows, especially where you don't have a shared file system. -- capture is going to spool the standard out and standard error separately for every single task that gets run. So if we go to, we skipped over that. Let's talk about basic capture. And I've got the job script here. I'm actually going to transition over to my other window where I have my CPU job. And instead of submitting that with sbatch, I'm going to just kind of do it interactively so I'm not throwing away my allocation. So let's go back to basic capture output. And yeah, so my task.in, uh, yeah, so the one, two, yeah, these tasks are just echoing a number. Um, so if I were to HSX my task.in, and all we're really doing, mm, yeah, I only have 12. Okay, so there's I've got a mismatch here, I think, between my intention, because I marked that as having 42 workers. Um, that is no matter. We're just going to be on a smaller scale. So I'm going to define my Hypershell site to just be my current working directory. And I will execute my task.in. And the only thing that I'm adding is dash dash capture. Again, no output shown because we're capturing the standard out and we don't have logging turned up. We'll do that in a minute. We kind of recover the same behavior. So there's our warning that was on standard error. So that came back to us, but the standard out was isolated. Um, there's a lot of stuff that Hypershell wants to govern around data. Um, inside of wherever your Hypershell site is, there's this oh, there I've got a lot of outputs there. Uh, Let me lib task. How many do I got? There's my 48. Let me let me delete those and then do that again. All right, and all right, I have an individual .out and .error file for each of those 12 tasks. Now, at the moment, this isn't really helpful, right? Because I've got this inscrutable UUID that doesn't really indicate where it came from. It's not really like the intention here is not for you to actually really care about where the output went. This is intended to be a unique location that is recoverable using other tools. So the goal here isn't for you to have to track this per se, but at the moment, if you were logging in more detail, you could look at the UUID there and then go find the file. For the time being, let's just look at those output files. There is our 12 lines of output. We're going to talk more about output management in a minute. All right. Bill, how are we doing? Is there questions that I need to look at? Nope.
No, no questions yet.
Okay. So let's scale up here. And I'm going to do this first one. The next one I'm not going to do live just because I don't have that kind of resources. One goal here is to be able to more efficiently scale to large numbers of nodes. So in this scenario, the thing that we're going to contribute to the conversation is an understanding that there are explicit client threads that are running that up until now, the Hypershell server and the Hypershell client have been a within process thread. But the whole system is constructed explicitly of this single server, many client concept. And we could launch these clients on another server and have them connect back over the network as their own processes running on other machines. The Hypershell cluster program, or HSX for short, is meant as a convenience to assist with launching these and orchestrating these collections of pieces. Later on, we're going to sort of decompose those intentionally to get more sophisticated behavior and fault tolerance and the like. But for now, what we want to understand is something called the launcher. So there's two main notions of a launcher in the Hypershell system. One is explicitly called out as SSH. So these are kind of exclusive modes. Here, if I said HXX help, I've got three modes. Really, there's only two. There's one called SSH, which functions, I imagine, kind of similar to how GNU Parallel works. It accepts a pattern of hosts. You can define collections of hosts in your configuration file, which again, we haven't talked about the configuration file. We will in a minute. But you can refer to a collection of host names by some group identifier when you're launching your cluster. And the difference here is that there will be a separate sort of process forked for each instance of SSH. And this is really meant for sort of convenience at smaller scales. If you've got a small collection of servers that is not an HPC cluster that is configured with a scheduler. For our conversation, we really only need to talk about a cluster environment where we have something like Slurm. So the --MPI is really only shorthand for setting your launcher equal to MPI. And this mode is very different from SSH, where we're forking a process for each instance that we're launching. In this case, we're only forking one process, and we're delegating to some other program on the system. And that program's responsibility is explicitly to bring about a distributed collection of processes in some kind of cluster environment. So MPI's job is to bring up that world. srun is very similar. And this is kind of like I'm sort of unapologetic here that it is not the intention of Hypershell to actually know or care what Slurm is. There is no mention of Slurm in the code. There's no mention of any scheduler. It's not Hypershell's job to try to build the whole world about how to bring about where these clusters come up, where these clients come up. We're just going to delegate to something else on the system. And for us, the most common thing to do is to delegate to Slurm. So in this instance, what I want to call out is the fact that now we're running on 8 nodes. So in my directives up here for SBatch, I've got N8. So we've got 8 nodes. And our cluster, yours might be different. Our cluster has 192 physical CPU cores. So essentially, I've got 8 whole nodes all to myself. And the important thing here is that, at least for now, there is only one Slurm task per node. So one of the issues with GNU Parallel about scalability is there's no sort of two-tiered scheduling going on. Every single task thread is at some point essentially a denial of service attack on the main GNU Parallel process. In our case, our clients are a world unto themselves, and they don't necessarily communicate back to the server for every event that happens in the system. So what we want to do when we're writing a job script is have one Slurm task per node, so that when we say launcher equals srun, essentially what we're doing is srunning the HS client. And actually, I'll turn up logging. I've added that bit. We'll get to configuration in a minute. We can add this as an environment variable, and it'll literally tell you what the invocation that it made was. And we're just going to bring up a bunch of clients and connect back to the server. Okay, so let me try to do that. Basic multi-node. I've got 100,000 tasks, 100,000 lines in my input task. These are a little bit more sophisticated, where again, we're just going to sleep for 1 second and we're going to echo true. But we've added a hostname invocation to the command line just to sort of track where this thing happened. Okay, so we've got our 8 nodes. Again, if I srun hostname, you could see anything that I srun, it's going to bring up that program on another machine. So I've got my task.in. I'm going to say 192. Um, uh, yeah, B192 launcher failed. Yeah, da 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 da. Okay. Oh, I need to export. I'm going to say force color one and logging debug. I will note this force color thing. There's lots of colors in the logging output, as you'll see in a moment. By default, if it detects that you're redirecting output or that the thing it's connected to is not an interactive shell, those will get turned off. For the purposes of this conversation, I'm going to force them to be on so that the output isn't like weird looking because we're connecting from other nodes. So let me run this right here. And I think this is correct. Now, for this example, I'm not going to say dash dash capture because I don't want to assault 200,000 files. Our Scratch file system absolutely could handle that, but I don't want that to be a bottleneck. Um, yeah, here we go. There. So um, I have not captured the output like I had intended here. So I'm going to kill that. Yep. And I'm going to redirect to task.out. So instead of capturing, we're just going to have all of that flow into one place. On a single process, you could say dash O, but that doesn't work in a distributed fashion. So we're just going to say task.out. Try that again. This will run for just a minute. Um, I suppose I'll just go over to the GitHub repo right here, basic multi-node. The thing that I want to call out as this runs is that with that output, we could do something like this, where we just took all the lines from the output and cut out the host name and sort of did a sort and a unique on there. You can accumulate a tally of how many of these things ran on which machines. So the goal here with this exercise is to run a much larger workflow across multiple nodes and um, sort of recover some information about where they ran just to see that, these are kind of equitably distributing across multiple nodes. Okay, so I'm not actually going to run this because I didn't reserve 1,000 nodes. Um, Again, finishing, so we're going to sort of transition here in just a second now, but finishing off the conversation about scalability, um, in a longer conversation, I might draw an architectural diagram to try to showcase what makes this setup different than what GNU Parallel is doing. Fundamentally, the distinction here is around task aggregation and communication. So every single execution of the task is not communicating with the server. What's happening is not only that the clients are accepting tasks from the server and running them locally, um, but there's this notion of a bundle, which we used on the last exercise, but I didn't call it out explicitly. So what's happening is that the server, both whether there's a database or not, is accumulating tasks in a preferred aggregation size or bundle size. And it's got a timeout there just so that it doesn't get stuck forever. And so it will flush tasks if a certain amount of time is exceeded. But it's accumulating a whole collection of tasks before shipping it off to a client, and that client is executing it locally. and there's not this communication back and forth at every turn. And what that buys you is at least another order of magnitude of scalability, just because you're not handling every single thing inside the server as it's running. So I have had this up to 3,000 nodes before. Our Anvil cluster, our access resource, is 1,000 CPU nodes, give or take, depending on which ones you count. The main partition is 1,000 nodes. And I've got 128 physical CPU cores. In my testing for throughput and efficiency, I sort of doubled up on that and oversubscribed it. So I have had up to 256,000 workers in parallel, and that's without bogging down the server. The other important thing is at this scale is this problem of all of your clients coming and knocking on the door at once. This can be one, it can just fail, and two, it's disadvantageous for sort of the cadence of the workflow. You don't want things waiting around and bottlenecking on that sort of metadata synchronization. So there's this flag called delay start. If you provide an integer number of seconds, then that is a fixed delay, not unlike the delay option in GNU Parallel. Only it's for the clients, not the individual jobs. With a negative number, it means a random interval between 0 and that value. So what I'm doing here is basically staggering the scale up process over 30 seconds. At the largest scales, you might actually want to do that over 60 seconds. And it can actually be helpful to pick something congruent with the size of the task. So if you've got single core tasks that are a minute in length, picking a startup delay of 60 seconds kind of helps even out that communication so that it doesn't bottleneck and have this sort of churning effect where there's just this flurry of metadata activity and then it's silent and the whole thing is sort of hung up on that synchronization step every minute or so. Okay, so that's enough about the sort of first in, first out situation. Let's get into more things that are unique to Hypershell. Yeah, okay. And do we have any questions? Nope. Okay. So up until now, we just used environment variables. We didn't really set up a configuration file. As I said before, there's a lot of things that you can, actually most things can be set in a file. This is going to be some cascade of options. There's a system level, a user level, and a local or project level config. This is kind of very similar to how the git command is set up. It's sort of inspired by that. So what we did before with the logging level, we could do here. So I'm going to pop over here outside of the job for a second. And um, our config command has a bunch of subcommands. And for starters, we don't have any files yet. It'll automatically make it for us. So if I remember to use the word set. All right. So now that is a global setting in my user level configuration, and I don't need to worry about setting an environment variable. The underscores on the environment variables kind of align with the hierarchy, if you can think of it like a dictionary. So anything that you set, you can ask where it's coming from. So everything has a default value. In this case, the default logging level was warning. Here, I've set it to debug so that I can see all the goings on of the system. There are deeper levels below debug. Just be warned that that's a lot of output and a lot of churn of all the machinery and the polling behavior inside that maybe you don't necessarily need to see if there's nothing going on. Debug is a pretty good level for if you have a pipeline running and you just want to know when things happen. So which config which is telling me that I'm currently set at debug, and that came from my user configuration and what the default value was. I can set things myself by just opening up the file. So it just made this for us. And the thing that I'm going to do now is set a database. So we haven't had one before, but I'm going to make one now. You can put this anywhere you like. I put some notes. So I've put some notes here. Um, for the database that kind of outline what I'm talking about, along with a warning about the file system. So there's two databases that we can use, either SQLite or Postgres. Both of them work the same way. SQLite, if you're not familiar, is an embedded database that runs in process and is quote unquote just a file on the file system. Postgres has some benefits around scalability and availability, better concurrency of like if you've got, I mean, this is a highly concurrent application with lots of reads and writes happening very quickly. Postgres handles that a little bit better without running into issues with file system locks. And it's also available over the network. But for a lot of people, SQLite, I mean, it'll get you really far, millions of tasks with no issue. But the only note here is that if you put that on something like Lustre or some other networked file system, depending on which one it is or how that's set up, you might run into issues where the cluster will crash because SQLite couldn't acquire a lock on the file because multiple nodes are trying to talk to that, or conceivably could. So just a note, your home directory is probably fine. We run ZFS. So I like to nestle that inside of my site directory just to keep things tidy, but you could put it in /temp or somewhere else. Okay, so I have just set that. And so now I don't need to say that dash no DB anymore. And now it kind of changes the tone of how we can run our workflow. And we've decoupled, and instead of doing this like monolithic start to finish all or nothing situation in memory, we can separate out the idea of submit versus scheduling versus execution. So with Postgres, you'd have to run a initdb. For SQLite, this happens automatically. You do not have to do this. It just happens. There's no explicit step to initialize anything. SQLite happens without you having to call that. Yeah,
Oh,
so
Jeffrey,
yes,
got a question.
yes.
What's the relationship between running Hypershell and having or requiring root access?
There is no requirement for root access. Everything that you run can run as a user. The database file is going to be on the file systems in some place like your home directory, and you're operating inside of the cluster environment just like you would run a Slurm job. Yeah, there's absolutely there's no infrastructure. Here in a minute, we're going to get into sort of more exotic ways of standing up pieces of this system, but in no uh, there is there is no scenario where you need site center staff to stand up any kind of infrastructure for you. Does that answer the question?
I believe it would, but I was relaying for someone else, so
Yeah. Okay.
maybe they'll do a thumbs up.
Yeah. All right. Good question. So if I go back here, um, we haven't talked about listing the contents of our. Oh, I'm going to pretend that I still have this left over from earlier today. So pretend that that didn't happen. So I have nothing in my database. I just defined that for the first time. And in order to submit something, we are going to use the submit command. And there's a lot of options here, but the easiest thing we can do is just give it one command line. Basically, the syntax here is if there's multiple positional arguments, those are treated as an argument vector. So we just submitted a hello echo hello world. All that happened was that got recorded in the database. I don't have any cluster running. There's nothing anywhere happening that would execute that. I would have to run all the pieces in order to get that to execute. I can um, kind of jump the gun here and say restart. And it will have seen that, executed it, and start. Now, I didn't capture the output of that. That just got recorded right here. Um, but it saw that that task was there, one unfinished task. It scheduled it, and then it shut down. So with the cluster, instead of providing a collection of things to run in sort of a like a one-shot sort of situation, you can also say restart, or you can even say forever, which means exactly what it sounds like. If I run restart again, in a matter of 2 seconds, it checked the database, saw that there was something there, realized everything was done and there's nothing to do. And so you can imagine putting this in your job script instead of what we did before, where really what you're doing is submitting a pilot job that just picks up where it left off. And having a database in the loop now means we can do much more sophisticated things about retries, and anything that got interrupted or orphaned or failed can just get picked up on the next run of the job. And even while the job is in the middle of running on some other node, this is just a SQLite database file on the file system. So even while the job is actively running, I could say HS submit and it would work out just fine. Um, the other thing we can do is say um, a file path, or I guess I'll uh, in the example here in the GitHub repository, I call out a situation where you've got some kind of a script. So the logic here is that if there's only a single positional argument and it finds that thing on the file system, if that thing is an executable program, then it's treated like a single task or a single job. If it's not an executable program, it's just a text file, then it's treated like a manifest in the same way that our input task file was before. So here I just embed that sequence thing, um, and I can say like this, and all of those get submitted. So that submitted 100 tasks now. And I've already talked about restart. Um, I'm not going to run this. In the interest of time, I'm not actually going to run this example. I did have an allocation set up for this. I just want to talk for a minute about one of the use cases here. Now that we've sort of broken down the pieces and we've got submission, I'm going to talk about like server client here in a moment. One scenario I want to call out explicitly that is a really big deal for us, and I'm sure is a big deal for others, is as compute is moving in the direction of having discrete accelerators in the box, as it were. Um, a lot of our performance numbers on the top 500 list are coming from GPUs or something similar to a GPU. These are very expensive resources, and there are commensurately large AI models that require those, but there's also a lot of throughput computing tasks that benefit from accelerators, but themselves are not large enough to justify such a large GPU. And what's happening is instead of having like a whole sort of landscape of different right-sized GPUs, we just have a whole bunch of the very largest GPUs. And the problem with throughput computing is that the sort of size or the granularity of the task, like an individual thing, is too small for the size of the GPU. And most of the main schedulers, for example, Slurm, treat these devices as indivisible discrete units. And so it doesn't allow subschedule, like you can't submit a job array and say, I only need a quarter of a GPU. It can only subdivide down to one GPU. And you could kind of pull this off with GNU Parallel, but similar to what we said before, it'd be really clunky. Somebody coming along afterwards would probably be annoyed at the sort of complexity of trying to define the parallelism inside of your job script. The value here that Hypershell would provide is that you could ask for one Slurm task per GPU. And then when you said dash dash launcher equals srun, you would have one Hypershell client per GPU. And then your parallelism on the Hypershell client level would be however many tasks, like how many you could fit on a GPU. So in this example, I've asked for two GPUs with one task per GPU, right? These are, at least in our case, these are like very large 80 gigabyte NVIDIA H100s. And a lot of the researchers that I work with can fit a dozen or more of their tasks side by side on that machine. And so I can pick a level of parallelism per GPU commensurate with however big my individual task is and accomplish this kind of sharing very easily without some long convoluted script. Um, so yeah, I'm not gonna go through the motions of that, but I just wanted to call it out as a particularly important use case that I see a lot of. Okay, so up until now, we've just run HSX or a Hypershell cluster, and we've separated out the notion of submit. So we could do a restart and we can submit things out of band and persist them in a database. But now I want to move into something a bit more sophisticated and talk about persisting a standalone server and separately bringing up clients somewhere else as necessary. So for the server, um, uh, again, here we've got a bunch of things that we can run. You'll notice that the command line options for the Hypershell cluster basically directly come from either the server or the client. And what it's doing is kind of sort of taking all of that and forwarding it to either the server or all of the clients. Here we're doing it explicitly. So bundle size, retries, and things like failures are handled on the server side. So what we want to do is we could say something like this, where R is short for max retries. Oh, I didn't mean to say -1. And down here, so I'm on one of the login nodes. This could be a login node. This could be somewhere else. There's two. Yeah, I interrupted it, so it's got two previous ones. Or the 100 that I submitted. Okay, so this is set to run forever. Um, Something that you should be aware of is by default, it uses localhost. This is not like a network training. In a nutshell, if it's set to localhost, then it's not going to accept outside connections. If you want it to accept connections from a different machine, like in a distributed context, you'll need to set that to 0.0.0.0. The thing I want to call out and that I have a warning about in the Git repo is an authorization key. So, or I'm sorry, authentication keys. So the cluster did this for you. If we scrolled back through the logs when we ran the cluster, you'll see this big long cryptographic string that it generated. Now the default is there, so it works, but it's not secure. So what we want to avoid is somebody else connecting to our cluster and stealing our tasks, probably accidentally, because they're using the same port. So I've set the super secure key my pass. Um, Here in my bottom pane, if I connect to my server running on login 07 and I said, foo, it's going to tell me that that key doesn't match and it's not going to let me talk to it. So if I say my pass, capture, um, now as it connects, it starts running. Now, of course, uh, I didn't plan that really well. That broke because my tasks were just integers and I didn't have a template. So let's do that again. I got all those nasty warnings because I didn't have a template. But let's submit another set of tasks, but this time we're going to apply a template at submit time, and these won't fail because they're just going to echo. Um, And now that I've submitted those, you see the server picked them up, it scheduled them, the client received them and started running them. Okay, so we can do this. Task management. In the I won't spend there's a sort of a long, rich conversation we could have about the capabilities around introspecting your job history and what sort of information is stored, how it's stored, what sorts of things you can retrieve, how you can structure those and update them. But I just want to spend one moment here to try to sort of illustrate what's going on. So let me kill this stuff. So I just killed the client and the server, and they're no longer running. The Hypershell list command is kind of our way into the database. Whether or not this is a SQLite or a Postgres database behind the scenes, it is going to translate that for us and recover our task history. There's a bunch of high-level stuff for common scenarios, like only being interested in things that failed, succeeded, completed, or things that are remaining. Um, but generally, if you don't say anything, it's going to turn all the data. Otherwise, but you can say what field you want. What I'm going to do to start off with is just say limit one. And that's just going to grab the first thing that it finds. And I haven't said how I wanted this formatted. The idea here that I want to illustrate is just what data is available. So you've got your unique ID, the input arguments. In this case, they're the same, but the point here is that uh, the templating is sort of a product or it manifests either at submit time or at the last second, uh, wherever the client is. Oftentimes, the thing that we want to submit is a file path or like an integer value or something like that. We can sort of recover what the original input was versus the exact thing that executed on the shell. I think yeah, in all these cases, these are going to be the same because I haven't sort of uh, set it up differently for the example here. We get the exit status, when it was submitted, when it was scheduled, when it started, how long it waited, when it finished, and how long it ran. In this case, it ran so fast that there was just no data there. This is normally reported, or this is recorded as some integer number of seconds, I think. Um, there is the submit host and a unique identifier for that host, so you can separate out each instance of the application. Where the scheduler was running, or the server and the client. In this case, these two IDs are the same because this first one we ran dash dash restart with. We haven't retried anything, but this tells you which attempt number that was. So if this had failed and we had retries enabled, there's a limit to how many retries it might try to do. And so this records what the attempt number it is. And what happens is if it retries it, it does not just, It does not overwrite anything in the database. What happens is if a task fails and it tries to reschedule it, it creates a new record and it will refer to you the previous instance of it. And if it got scheduled again, what the next instance of it was. Um, Now we didn't have anything here, but I think if we look at not this one, but one of the other 100, we said capture. I mentioned before about captured output. There is an out path, and the output and the error path that's recorded in the database. The idea here is that you shouldn't really care where it is. It's somewhere down inside the Hypershell site. This should be a recoverable attribute that you could grab back. So let me look at a few of the others to get their IDs. So let me say list, I don't know, show me the ID and the args and format it as a table, limit 10. Okay, so here's, oh, those all failed. Let me say order by submit time descending. So here we go. So here's the last one. You can filter. So I could say like where ID equals something. You could also say info with an ID, and it's the same thing. And notice it at this moment we had enabled output capturing. So you could say dash dash standard out. The thing I want to point out here is that it's not merely that it's going and finding it here on the file system and dumping it back. There's an added layer here in case you're running an environment that does not have a shared file system. What happens is this output path is the output path relative to the client. So in our case, I have a shared home directory file system across the entire cluster, but like maybe in a cloud context, that's not the case. And all of the nodes, if you're operating in like /var, don't have a shared file system. What it's going to do anytime you're asking for output is this UUID allows to have a universally unique location no matter what across all clusters across all time. And so if it doesn't find this output path locally, what happens is it will go to the client and it will use it will create an SSH connection, and over FTP will bring that back and cache it locally and then display the information. And if you do it again, it's already cached, and so it just displays it initially. And what that enables is for you to do things like Hypershell. There is a wait command. If you submit a task and you have some part of your workflow that should wait on some other thing being done, you can say Hypershell wait with an ID, and it will just block until that thing finishes. And what that allows is for this higher level run command where I could say Hypershell run, echo hello world, and that would submit the task, wait for the task to be completed, and then bring back the standard out and standard error and dump it here as if it had run here. Okay, so yeah, uh, count is very helpful. If you're just interested to know like a status update of where the thing is in the workflow, you can just list how many you have remaining. What I haven't really talked about yet is tags. I've got some stuff here in the slide deck about managing your workflow, both for the execution of the flow, but also tracking things in your task history. Something that kind of came out of the work that we did with researchers is just wanting to be able to recover bespoke collections of things. And so there's this rich user-defined tagging system where when you submit something, you can define a tag. as well as in your input file I'll show in a second. And this is like a key value system. So we're using this colon syntax, but if there is no colon, then it's sort of empty. So you can have a sort of a flat tag here. So in this case, I'm submitting these 100,000, these 1,000 tasks and tagging all of them as belonging to some hypothetical group one. It does understand types. So this one is treated as a one, not merely as the character. So you can accomplish a lot with that. So this is it's not going to just nakedly try to match that whole thing. By having a sort of key value based tagging system, you can do a bunch of things with that that are really helpful. So we can not only recover the group, um, but I could say um, group one, and then I could say group two and group three. And as I'm looking for things, so there's six out of everything I've done over the last few minutes, there's 601 things in the database. If I say without the colon, that means anything that has that tag. If I say with the colon, it means specifically that tag and that value. So you can accomplish a whole lot with this. Um, One thing that I ran into that's a recent addition is the fact that this can be somewhat cumbersome if you've got like if you want to really take advantage of this and have lots of very specific tags, like in the example with GNU Parallel, where we have those combinatorics, and you've got, for every 10 of these, you've got 10 of the like parameter A, parameter B, parameter C, and parameter D. You want all the combinations of those things. It can be difficult to try to manifest that. Um, uh, you don't want to be submitting them one at a time because you want if you're submitting 100,000 things, you want the transaction size to be efficient. And so what we've added is um, inline tagging. So this has been around for a while. So kind of like your SBatch directives or your, whatever your main scheduler is. If there are comment lines, those get parsed at submit time, and it will extract the tagging assignments in there. So in this case, um, in addition to the UUID that each task gets, it's going to grab. We're sort of assigning the input argument so that we can deal with that effectively. But in addition to these, there's also group levels. This is a new addition. Um, it can be helpful to have like bunches of things, and you can combine all three of these at the same time. So this is really helpful. Um, all right. Now, in addition to searching for tasks, oftentimes what you want to do is modify something after the fact. So how do you change the database once something is already in there? There is another command called HS update that has a lot of the exact same command line switches that the search capability did. And here, what we can do is there's some high level stuff. Um, like cancel, revert, and delete. Delete actually just removes it from the database. Oftentimes, that's not necessarily what you want to do. Revert kind of nullifies everything so that it's like it's a novel task, like it's never been run before. And cancel leaves everything as it is. It just marks the exit status with a -1 so that it doesn't get scheduled, but the information about it is preserved. Um, you can update bespoke things like, if you want to change the argument, the example that I have is this would find anything that had an input argument of 42 and change it to have an input argument of 7. So all of the positional arguments are sort of assignment like. But you could also use the tag, like the colon syntax for tags, and say like data 42. So this would everywhere in the database where the input argument was 42, it would add a tag with that. But you could also just say something like, oh, I forgot to apply a tag. I'm going to um, let me see. What do we have? Tag keys, values, group. We have 1, 2, and 3. Let me say I want to update and say um, apply group 0 everywhere. I don't know. We could say order. You could even do things like order by submit time limit, 301. So those first 301 things I did. Um, what's interesting here is that you can target based on sort of proximity to other things. So this could be really handy to like fix things afterwards. All right. So in the time that I have left, um, I want to talk about auto scaling before I run out of time. Um, One of the really nifty things here with the notion of like having like separate server versus client is that clients can come and go. So there's sort of two mechanisms that I'm really jazzed about with Hypershell, and that is this sort of dynamic elastic scaling. And we can accomplish that as sort of a first class citizen, but also we can sort of build our own deployment ourselves, which is the next part. For auto scaling, there is actually a flag called auto scaling, and there's two policies, fixed and dynamic. Fixed means I'm going to bring up some number of clients and I'm going to try to maintain that. And if any of my clients disappear, I'll notice, evict them, reschedule those tasks, and bring up a new client to maintain that size. But the really interesting one is a dynamic cluster, which I just for the interest of the slide, I've used shorthand notation here with single letters. Um, but the longer form arguments are a little easier to understand. So with a dynamic cluster, essentially what we want to do is have some initial size, but we actually want to let the thing go to 0 because if there's nothing to do, we don't want to be churning on, jobs and scheduling and just having the node sit idle. That doesn't make any sense. But we might want to set some maximum size as well. Like we don't want to go we know that we're only allowed to schedule up to some number of nodes, so like don't try and put something in the scheduler beyond that. The thing to understand though that is maybe unique here is this concept of task pressure. So there's this dimension, this quantity that you can define called your factor, that if you look at the manual page or the website, it sort of walks you through what's going on there. Essentially, what's happening is if you have some number of actively connected clients running tasks, you can calculate some sense of a time horizon that says, in units of my average task duration, how many scaling units, like when am I going to finish given the current size of the cluster? And the scaling factor is how many of those scaling units away do you want to prompt another, you want to scale up one more unit. So a scale factor of 1 means if, given the current number of connected clients, my average task duration, like if my average task duration is like a minute, if there is more than a minute remaining given the current landscape of my cluster, then add one. Otherwise, just let it be. I know I still got tasks, but don't bother adding one because I'm almost there. So let's run that. So what I've done here is basically say I want a whole node, single core tasks. I want a scaling period of 5 seconds, which is very aggressive, but for illustrative purposes, we're going to go with 5 seconds just so we can see it think. We're going to initialize ourselves with a job. Maybe we could change that to 0. We're going to allow ourselves to go down to 0. We're going to allow us to scale up to 12 nodes. We're going to have a client timeout of 60 seconds. So if a client is idle for 60 seconds and there is nothing available, it'll shut itself down automatically. And we're going to use srun, this more complicated srun invocation as a way of bringing up our client. Now, I want to point out that this is not the same as what we were doing with GNU Parallel. We are outside of a job context, so this is going to bring up a task. We are not doing srun invocations per task. This is only getting us our node in a pilot job fashion. And the last thing that I'm really proud of here is this Unix signal. So Slurm has the capability of sending a signal. So we use the SIG USR1 to signify a sort of drain signal. So this says 10 minutes before um, 600 seconds or 10 minutes before I hit wall time, send a signal to tell it to gracefully shut down. And this avoids wasted cycles where um, you're going to start on a task that you know you'll never finish because you're going to run out of time before the average task duration. So like just like finish what you have now, but don't take anything else and just shut down gracefully. So I'm going to okay, ML set. So I just said echo hello world. And of course, it is throwing up all over all of those things because it had stuff in the database. So I'm going to clean that up. There we go. We start that again. All right, there. It scheduled that task. We'll see that start here in a moment. Here's our one instance. Let me close these. There we go. We get rid of those. There we go. Yep. So, yeah. In the interest of time, we won't sit here for longer, but essentially what's going to happen is um, like if there's sufficient tasks to justify the client to continue to exist, it will. If there's not, it'll shut down. If I submitted a large number of things, like if I said submit 1,000 things, uh, now this is probably on the one node, it's probably going to finish it. But the point being, if I gave it a very large volume of things, you would see it start to add more workers. Okay. Um, Lastly, instead of using the built-in feature, something that I've arranged quite a bit at Purdue so far with a number of different sort of core, what I'll call core facilities. Um, what you can do is take the Hypershell server and use it with a Postgres database instead of SQLite and deploy that in a dedicated environment off cluster somewhere else. So in our case, we have a private cloud environment that sits next to the HPC, and it's not a Slurm cluster, it's a Kubernetes cluster. And so I've got a Dockerized version of Hypershell running the server in a persistent fashion available on the network there, alongside a Postgres instance in Kubernetes that the server and the clients and my laptop can talk to. And so like that is always on and it can remain active for, a year, 2 years, three, however long. And what we're going to do is submit pilot jobs as necessary. So that's what I have here. I've got a little job script that's sort of this minimum viable version of this. And now this is going to be different for you. So I've modified this as sort of like a, whimsical sort of, you've got a university.edu. But I've got this X core, X, X marks the spot, X is the unknown. I've got some core facility with a service account, username xcore, and I've got a DNS, like I've got a network subnet for xcore, and I'm running the Hypershell server within that, available over the network. And in a similar fashion to what we were doing with dash dash autoscale, we're bringing up clients inside of a job. In this case, this is just part of a node. So just 48 cores, and I've got 48 here. So basically, I want to be able to elastically bring up resources for a large volume of single core things. And in order to put this into practice, I need another piece, another component that I call xcore autoscale, which is just a script. In practice, this is way more sophisticated, or it can be. But here's sort of a minimum viable version of that. Basically, what we're going to do is just ask Slurm, um, like, give me a list of all of your currently running or pending jobs with the Xcore pilot name. How many of those do I have? And then I'm going to take Hypershell and ask, like, what is my count of remaining tasks? And I'm kind of implement the same task pressure concept that Hypershell was doing on its own, and try to make a choice about whether or not I want to add another scaling unit or another worker. And in doing so in this fashion, you can have a persistent deployment that's running off cluster somewhere, and it's not using any resources on the HPC at all. And then from some other workstation, it could be a lab machine or your laptop, you can just say HS submit from another machine and just trigger work to happen. And as those populate the database, this script will, the server will notice those, offer them up on with the scheduler, and this auto scaling script will notice that those tasks and spawn workers as necessary. And it's like this is, well, this is there's a few moving pieces here. This, like, why not just use Slurm? Going back to what we talked about earlier on in the conversation about all the hangups with the main scheduler and the problems with throughput computing. Basically, what you can construct here is your own private scheduler outside of Slurm and elastically scale your own cluster as needed. So that's everything I wanted to get to. There's a lot of stuff that I could touch on, but that's sort of the gist of it. So I'll leave it at that.